Good morning, everyone. Welcome to lecture 2 of Statistical Methods in Cosmology. So I will continue introducing today some relevant ideas in probability and statistics, in particular ideas that are useful from the point of view of a cosmologist. Okay? So we will see now, I will be introducing the Bayesian and frequentist interpretation of probability. And I will give some examples so that we all understand well these two approaches. Okay. Great. So what we will be doing is going over Bayesian and frequentist interpretation of probability. Great. So basically, the Bayesian and frequentist interpretations of probability are two principal approaches to statistics. Okay, the frequentist interpretation is that basically defines an event's probability as the limit of its frequency in a large number of trials, okay? A frequentist basically observes an event, a large number, unfold many times, and in the limit in which the number of times of this event goes to infinity, the frequency of its outcome becomes the probability, okay? So I will write down that the frequentist defines an event's probability, as the limit of its frequency in a large number of trials, as the limit of its frequency in a large number of trials. Okay? What about the Bayesian? Bayesian, so this is one. The other is the Bayesian approach, okay? The Bayesian interpretation of probability basically is based in the degree of belief in a hypothesis, and not on a frequency, okay? One of the crucial features of the Bayesian view is that a probability can be assigned to a hypothesis, which is not possible under the frequentist view, where the hypothesis is either accepted or rejected, okay? So the Bayesian assigns a degree, Bayesian defines an event's probability based on, I will explain mathematically what this means, okay? Based on the level of belief, this may sound not well defined right now, but give me 1 second. On the level of belief in a hypothesis. Okay? So these are the two different approaches. So for example, for a Bayesian, I don't have this. I started with in the end. Okay, I thought I started in the beginning, so I will start. Okay, so for a Bayesian, the data are fixed and the model is repeatable. And for a frequentist, the model is fixed and the data are repeatable. Okay, so Bayesian, I will give some examples of this. For a Bayesian, data are fixed and model is repeatable. For a frequentist, the opposite. The model is fixed. The model is fixed, and the data is repeatable, okay? Okay, great. I don't know what this is, but it's okay. Great, so, you know, I'll give you some examples now, but people tend to say, oh, I'm a Bayesian, or oh, I'm a frequentist. I don't claim I'm any of them. It depends on the problem that you're studying, the type of approach you choose to follow. You know, in general, it depends on the question. Sometimes I use the frequentist approach. Sometimes I use the Bayesian approach. For example, let me give you an example of how a Bayesian and a frequentist may study a particular question. So let's say I would like to measure two cosmological parameters in the universe, omega matter and omega lambda, to say something. So let's assume two parameters, okay, for simplicity. So, and let's say, yeah, so what would the two, and for a particular data set, I don't know, supernovae data set, okay? So what would the two type of approaches be? So a Bayesian basically would take some prior, say, I don't know, you could take uniform prior in omega matter and in omega lambda, some prior. Then for each model, and by this I mean for each point in parameter space, omega matter and omega lambda, you compute the likelihood of the data, okay? And then you know, varying, for example, using, for example, the chi-square statistics. You compute the likelihood for the data, and then you use the so-called Bayes theorem, which I will explain in a little bit, for the probability of the model given the data. Okay? And this is based on the level of degree, as we will see, that you have on a certain hypothesis. Now, what would a frequentist do? A frequentist can calibrate his or her statistics by assuming a model. Say they assume omega matter is equal to omega lambda is equal to 0.5. I don't know, that's a model, okay? You run many realizations of whatever data set you're considering. Say you consider supernovae data, okay? You fix the model, you run many realizations of your data. Each realization of the data will give you some chi-squared, okay? And then you histogram all the chi-squares, okay, for each realization of your model to calibrate the likelihood. And so then you calculate the chi-square statistics of the real data, assuming, you know, the same model and compared to the histogram. And that's basically, this will give you a relative likelihood for that particular model. And then you can repeat considering many models. You see, here you fix the model, you run many realizations of the data, and you compare the actual observed data with these many realizations. The other approach is different. And you know, in cosmology, it's very common, at least for cosmological analysis, to use Bayesian statistics. So I'll do a little bit more emphasis on that because that's something that we will use, for example, when we study Markov chain Monte Carlo likelihood analysis. It's a very common way of doing parameter inference. All right. So how does the Bayesian, I talked about Bayes theorem, but I didn't explain what it was. So let me go a little bit in detail about Bayesian statistics, okay? Bayesian statistics will make use of the so-called Bayes theorem. Okay. Let me talk about Bayes' theorem. Bayes' theorem says the following. So let me write it down and I will explain each term, okay? So this will be the probability of the model given the data is equal to the probability of the data given the model times some prior probability of the model over some prior probability of seeing the data. This is what Bayes' theorem states. What does this mean? This is okay. So this guy, a conditional probability of seeing the data given that some model M is true, okay? This is known as the Bayesian evidence, okay, or the likelihood. This is the likelihood. This is the likelihood, also known as the Bayesian evidence. Bayesian evidence. What is P of M? P of M is the prior probability that we have on a certain model M, okay? It's the probability that we assign to a particular model M before seeing the data. You could, for example, I don't know, you could be measuring certain cosmological data set, and perhaps you know some others from another set of observations, so you add a prior here, okay, on the parameters that you know from before, or perhaps you think that a certain parameter has a uniform probability of being seen, so it's related to the prior probability that you have on the model that you're considering, okay, or the parameter that you're considering. And P of D is the prior probability of seeing the data under the model that you're considering. You know, in general, it's a constant, and you don't need to compute it explicitly in most cases, because you will be comparing different likelihoods or posteriors. So this guy over here, so this is the prior. This is the prior, okay? This guy over here is it's known as the posterior probability. Posterior probability of a certain parameter. Probability, okay, of a certain parameter. Basically, it's the probability of, yes? That goes under the prior. Yes, that would be a prior. For example, the tensor to scalar ratio, you know it's a positive quantity. Yeah, so you add it as a prior. You could add it as a prior. It could go from 0 to infinity. Yeah. Those are, you know, physics-informed prior, when you know something cannot be negative or you know, similar issues. So this posterior probability is a probability that the model is true given the data, okay? And so we are often interested in the posterior probability of a certain parameter given the data. And so, but we can often, what happens is that we are interested in this quantity, but we can calculate this quantity, okay? We can calculate the likelihood of the data given the model. So we make use a lot of Bayes' theorem to relate one to the other, okay? To go from one to the other, we use Bayes' theorem. Okay. Now, you know, it may happen that the likelihood is very close, it's very similar to the posterior probability. In that case, that is good news, okay? If that happens, it means that the data are very informative and the priors are not relevant, okay? However, when the data are not very informative, the choice of a prior plays a role, right? And that is, you know, that is when we are a little more in trouble, because the data are not being very informative, and the posterior that you get may depend on the different priors. So if you see that these two guys are not closely related, your data are not very informative, okay? That's a situation in which we never want to be in, but sometimes we are in that situation. Okay, so Bayesian statistics in general is useful for model comparison. We were talking about this in with Susana and Matthias in the coffee break about model comparison, okay? So let's say we have two models. So how do we do model comparison? So let's say we have two models, M0 and M1, that you would like to compare. Then what you do is you compare the posterior probabilities of this model. So these, okay. So how do you do model comparison? Model comparison. Let's say two models, okay, M0 and M1. You want to compare the posteriors of these two models. So you have the posterior of M0 given the data. You compare it. You take the ratio with respect to the posterior of M1, the data, and this is what? Well, you can see that this will be equal because of Bayes' theorem. This will be equal of the posterior of the data given M0 times the prior of M0, okay? The P of D, given that it's the same data set and I'm comparing two models, that will just will cancel out. So you can see one example in which that's not relevant. And here you write the posterior, the data given the model times the prior of the model, okay? So this guy, I can write it as, let's call it B01 times the posterior, the prior of model 0 over the prior of model 1. Yeah, this ratio of the data given model 0 over the data given model 1, this guy is the so-called Bayes factor, okay? Sometimes Bayes ratio. This is called Bayes factor. And it is the ratio of Bayesian evidence, okay? So, you know, we can see that the Bayes factor gives the factor by which the relative odds between the two models have changed after the arrival of the data, regardless of what we thought about it from before, okay? This Bayes factor is given independent of the priors that we have on the two models, okay? So it's the relative, you know, the ratio in which the factor by which the relative odds between the two models have changed when we saw the data. So the relevant quantity to update our state of belief in two competing models is the Bayes factor. Yeah, we use the Bayes factor. And we will see when we study Markov chain Monte Carlo likelihood analysis that we will use this Bayes factor as the relevant quantity to update, you know, our state of belief in different models. Okay, so I thought I would. Okay, any questions? Yes, Maria Pia. Yeah, that's a great question. So in general, there are different criteria that you can take into account to consider the number of parameters, right? Because you could have two different models, one doing better than another one, but maybe it has more parameters. So how do you fold this into account? So there are different criteria. There's, for example, one example is the so-called Bayesian inference criterion, in which you fold in the number of parameters of your two different models to penalize the more number of parameters, okay? In which you can do this. Yeah, great question. Other questions? Yes, Greco. The Bayes factor, yes, the Bayes factor is basically, it tells you the relative factor. It's just the ratio between the probability of the data 0 over the probability of the data given model 1, okay? So it's the relative odds of, is how it basically tells you the relative degree of belief that you have in one model over another model after you have seen the data, regardless of what you thought about the two different models from before. Yeah? Okay. Okay. So I thought I would talk a little bit about likelihood, since this is a course on statistical methods in cosmology. I will introduce likelihood. I will talk about central limit theorem. I don't know if you have seen it before here, okay? It will not be rigorous, but I thought I would tell you a little bit about likelihood before jumping in the full topic of modeling of data and statistical inference, for which we use the famous likelihood, yeah? Okay, so let's move on to this. As an example, I will be, well, you will see. Okay, so the next topic here will be likelihood. It's a must-have topic in a course of statistics for cosmology. Likelihoods. Okay. So basically, you know, there are different ways in which you can write. You saw what I call likelihood before, right? The probability. I wrote down when I wrote down the Bayes theorem, I wrote down the probability of the data given the model, okay? So there are different ways in which you can write down a likelihood function. And if you write it down analytically, it will probably be some approximation to the actual likelihood function, okay? Nowadays, people sometimes like to learn the likelihood function from the data using machine learning techniques. I will not talk about machine learning, I think, at all in this course, okay? So anyway, so let's make some approximations. Basically, I will take as an example the CMB. So let's say for the CMB, basically the CMB temperature distribution is nearly Gaussian, right? Besides, you know, some secondaries here and there, but we can think about the CMB primary as nearly Gaussian. Now, the CL distribution in general is not a Gaussian unless you go to high L's, yeah? Probably you have seen this with Julian last week, or yeah, okay. So what happens at high L, at high multiple moment or small angular degree in the sky? Basically what happens is that the central limit theorem kicks in and will ensure that the likelihood is well approximated by a Gaussian. At low L, this is not the case, and we were talking with Agustin about different ways in which you can do it at low L, but let's take the case in which we can make an analytical approximation, okay? What's the central limit theorem? Okay. High L, high multiple moment, okay?
Yes. By the central theory limit, it seems likelihood. I cannot write. Can you repeat again?
I'm just saying that, bear with me, I will explain the central limit theorem, but I'm just saying that at high L, it will be a good approximation to like the likelihood as a Gaussian. Okay, so what's the central, why is this a good approximation? What's the central limit theorem? Central theorem. Fundamental theorem that used in, you know, not only in cosmology, but everywhere in physics or other fields. So the central limit theorem says that, let's say you have variables, so x1, x2, blah, 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 xn, okay? And these variables are, you know, we have n independent variables that are identically distributed, and they are random variables, okay? So the central limit theorem says that as the sample size of these variables increases, the distribution of the arithmetical mean of these variables approaches a normal distribution with some mean and some variance. Let's say all the variables have the same mean. Well, the mean will be that mean, and the variance will just be the variance over the number of variables, yeah? But what the central limit theorem says is that when the sample size of this variable increases, the arithmetic mean of these variables will follow a Gaussian distribution. Okay? So, sorry?
Every x, if you have
It's a variable that is randomly distributed, and when you have many of these x's that are randomly distributed, you know, the distribution will follow a Gaussian. Okay? So at high L, you have different, more and more ALMs, right? Because you have 2L plus 1 M's modes for each L. So at very high L's, you will have more and more modes, and that's why the distribution starts, you know, the central limit theorem kicks in. When the central limit theorem kicks in, we can write the likelihood as a Gaussian. So let's say, you know, let's say we have the likelihood, we'll write the likelihood as a Gaussian. Let's say we have the likelihood of the temperature given theory model of CL. Okay. CL theory, I will write here. So this will be proportional to, well, I'll write it as a Gaussian, okay? This will be proportional to e to the minus t s minus 1 t over 2, and this will be 1 over the determinant of s. I will explain what these things are, okay? T here will be the vector of the temperature map, and CL theory will be the CLs given by a theory model, okay? And S will just be the signal covariance in this case. So what's the signal covariance? Well, you know, I will not write it down, but I will say that this is the covariance.
Is it the matrix covariance?
Yeah. Yes. And this is the vector of the temperature of the map, measured on the map. Okay. So in this case, you can write down the likelihood as a Gaussian. Now, you know, you may go and measure the data. You measure the CLs of the data. You have a theory model. So you can rewrite. Susana has a question. Yeah, so here you are including them. So here the theoretical CLs are included in the signal covariance. Yeah, I didn't write down the covariance, but let me write down the covariance. So Sij, which is the signal covariance, will be the sum over L of 2L plus 1. There are factors of 4 pi. I wrote them in my notes, CL theory. And this is the Legendre polynomials between two different directions in the sky. Okay, great. Yeah, thank you for the question. If not, I was not saying where the theory comes into place. So we can write, yes? What was your name again? Xiao. Yeah, you should include noise there. Yes, yes. Correct. Yes. So you can likelihood, for example, for the observed CN in this approximation as minus 2 log likelihood. Say you're just observing temperature, okay, as what? As the sum over L. 12 plus 1, and then you will have the log of CL theory over CL data. Okay, this is just following this approximation. I just want to give you an example. It doesn't look very difficult, so I just wanted to write it down. CL data over CL theory. Minus 1. Okay? Great. So this is, this is the expression of the likelihood that is a Gaussian for the CMB. You could also generalize it to take into account temperature and polarization. I will not write it down here, but it's you know, it's a trivial exercise to write down the covariance and generalize, one second, and generalize that likelihood when you compute, when you take into account temperature and polarization. Everything covaries there, so you have to take that into account. When you add noise, you can also add noise from the experiment. Zero noise, okay? So you take the CLs plus noise, plus, okay? Yes?
On the right fraction over denominator, CL power, I don't understand.
Theory. TH is theory. Yes. I wrote it differently, sorry. Theory. Yeah. Okay. Great. So, once we have some, you have a question.
So this law comes from the three-factor.
Yep.
You had one of the determinant. But the determinant was just theory, no? Wasn't it? Determinant of the covariance, right?
Yes, yes, yes.
Why do you get the ratio of theory over
No, one second. Wait, I do have, so the likelihood, no, you're right. The likelihood, no, so there is a log in both sides, right? So it doesn't, so there is a determinant, yes, but remember that the likelihood I wrote it as e to the minus t c minus 1t, yeah? So it comes from there. Over the covariance. So the covariance has the theory, but the t, the data is, yeah. So the theory and the data come from the covariance and the data vector that you're measuring. Yeah. Yes, question?
No, clarification.
Clarification.
The CL of the data, you include the systematic, the statistic, the noise, everything.
Yes, everything. Yes, correct. Javier, you had a question? No? Okay. Yes, Greco? You have a question? Yes. That's right, yes. No, nothing. I'm just changing, you know, I define the likelihood as a Gaussian, but then I'm just taking minus log likelihood just to avoid writing down the e to the minus blah, blah. Yeah? Yeah. No implication. Just to facilitate things. Okay, so now we saw the central limit theorem. Now we have a likelihood that can be well approximated analytically, okay? So once we have the likelihood function, we can start analyzing data, and we can start making, you know, modeling the data and making inference about different theories, okay? Making cosmological inference. So let's talk about what do you do to make, you know, let's start talking about statistical inference and modeling of the data, okay? Now I want to start talking about modeling of data and statistical inference. Okay, so given a set of observations, often you want to fit a model to the data, okay, where the model is defined by a certain set of parameters. Now, you may want to define, you know, you want to fit your model to the data, but you may want to define a merit function that measures the agreement between the data and the model. Those questions are relevant every time you do data analysis in cosmology. So by adjusting the parameters of your model to maximize the agreement between your model and the data, you can obtain, for example, the best fit model, okay? Or the best fit parameters of your model. And so basically, what do we want? Well, we want a fitting, some sort of fitting procedure that gives us, what do we want? We want to have the best fit parameters. In general, I will write down stuff that we may want, okay, from cosmological analysis. We may want best fit parameters. They want the error estimates on these parameters, okay? Error estimates of the parameters of your model. You may also want a statistical measure of the goodness of fit, okay? Some measure of the goodness of fit of the model that you're using to fit the data, okay? So you can ask, well, given a set of parameters, what is the probability that this data has occurred? And this is the likelihood, right? The probability that this data has occurred given a set of parameters is the likelihood. And how do you estimate the best fit model or the best fit parameters? By maximizing the likelihood, which is the function that I wrote before in some approximation, okay? It's not the only given function. I just made some approximation. Okay, so let me talk a little bit, perhaps you're all very familiar with this, or perhaps not, so I thought I should start from scratch, talking about chi-square, goodness of fit, confidence regions, etc. Okay, so great. So let me add a page here. So let's talk about goodness of fit, chi-squared, confidence. Okay, which is stuff that you may see written in many, many papers in cosmology when you open the archive. So let's say that we have some data points, okay? Let's say that these data points, we call them GI, okay? And you have some model with parameters. This model has some, it's a model of X with some parameters alpha, okay? So what is the least chi-squared? Well, you can write the least chi-squared. The least squared, you can write it as the sum certain. Sometimes these weights are taken to be 1 over the variance in each data point, okay, of what? The data minus the model, okay? The model may be a function of some whatever points you're considering, and some parameters, okay? These weights, again, are taken in general to be 1 over the variance on each data set. So the best fit parameters are the ones that minimize this chi-squared, okay? So to minimize this chi-squared, you will square this for you want to you want to minimize this chi-squared with respect to each parameter, okay? There should be a squared. Yes, thank you very much. I missed it. Okay, so if the measured errors are Gaussian distributed and the model is a linear function of the parameters, then the probability distribution for different values of this chi-square at the minimum is the chi-square distribution for some number of degrees of freedom. And those degrees of freedom are the number of data points minus the number of parameters. Okay? Yeah? So again, I say it again. So, you know, the probability distribution, if the errors are Gaussian and the model is linear in the parameters, the probability distribution for different values of chi-squared at the minimum, okay, which is what we are doing to get the best fit, is a chi-square distribution. I will write down what I mean by chi-square distribution for n minus m degrees of freedom. So it's a chi-square distribution for n minus m degrees of freedom, okay? Where this m is the number of parameters, okay? And n is the number of data points, okay? This is under this approximation where the function is linear in the parameters, etc. Many times this is true even if we break a little bit these approximations, okay? Now what is a chi-square distribution? Okay, this is of course in statistics for cosmology, but let me write down the chi-square distribution. So a chi-square distribution, you probably all know this, but just for the ones who don't remember it, chi-square distribution is given by, let me write it down. This is 1 over 2 to the nu, where nu, no, 2 to the nu over 2, sorry. This is gamma function, nu over 2. And we have this, 1 second. I will define what I mean by these quantities. E to the minus y over 2, okay? Nu is the number of degrees of freedom, okay? Here is the degrees of freedom that you are considering. In this case, it's n minus m, for example, okay? So what is the mean of a chi-square distribution? The number of degrees of freedom. It's nu, right? The variance is 2 nu, and so on. Okay, so in general, it's common to ask, for example, just to know the goodness of fit, it's common to set a threshold, okay, and ask, what is the probability that the observed chi-square is less than a certain value, okay, of chi-squared? So you can write down, I thought I would write this down in case it's useful. So the probability of the observed chi-squared, no, let me write, sorry, this is the chi, not an x. The probability of the observed chi-squared being less than a certain threshold that I impose. Okay. I will call the threshold with a hat, all right? That's something that we imposed. Well, the probability of this guy for new degrees of freedom, okay, here, new degrees of freedom. This is given by this incomplete gamma function, okay, for nu over 2. You can find these functions in Wikipedia always, okay, and this is the threshold that we impose, chi-squared over 2, okay. Gamma is the incomplete gamma function again, and you know, this is the probability of the observed being less than a certain threshold, and then you can calculate, you know, the probability that the observed chi-squared exceeds some threshold by chance, and this is 1 minus p, okay? Okay, so now you can take a look at those values of p and q, okay? And basically, you know, the probability q at the best fit model gives a measure of the goodness of fit, okay? So if this q, which is the probability that a certain chi-square exceeds by chance some threshold that we impose, if this Q is very small, something might be wrong, right? The model is wrong, or the errors are larger than expected, or perhaps they are non-Gaussian distributed. Something might be wrong if this Q is very small. If this Q is very small, the probability, of exceeding some threshold chi-square is very small. If Q is very close to 1, there might also be something wrong happening with the model. If Q is very close to 1, probability, okay, is very small. So, a general rule, the chi-square by I rule, is that the minimum chi-square, this is a rule of thumb, okay, but the chi-square of by I says that the minimum chi-square should be roughly equal to the number of data points minus the number of parameters, okay? That's kind of a rule of thumb of the chi-square by I. Yes, question?
Yes, I have two doubts. When we have the data, we refer to only one kind of coordinate, or for example, 3-point coordinate, x, y, theta, or just x or y?
I'm not understanding the question.
Okay. We have the data.
Yes, you can quantify it. Yes. So what's the question? If it depends, if it can depend on many
Yes.
many parameters? Yes. Yes. Mm-hmm. Yes.
And another question is, what is the threshold?
The threshold. The threshold is some value that you impose, okay? It depends, it's subjective. It's some value that you want to impose for the threshold. So you will see your chi-square distribution, you will see where you stand, you will impose some value, and you want to know if you exceed that value. Perhaps that value is on the tails of the distribution. So you want to see, is my model on the tails of the distribution or not? That's the kind of question that we are trying to answer. See, how unlikely is your model to happen? If it's very unlikely, okay, let me say it. Thank you for asking, because I will take the chance to say it in words rather than. So if your model ends up being in the tail of the distribution, where it's very unlikely, well, that's a bad thing, right? Yeah? So you want your model, so that's kind of what I'm saying with this. Yeah? Okay. Okay. So in general, it's useful to present confidence level limits. It's useful to calculate confidence level limits, and well, this is something that you see in every paper in cosmology and in other fields as well. So basically, a region in the m-dimensional parameter space that contains a certain percentage of that probability distribution. That's the confidence level limit. Okay, so I will start talking about confidence levels. Let me put confidence levels. Okay. So with confidence levels, we want to quantify a region in some m-dimensional parameter space that contains a certain percentage of the probability distribution, okay? That contains some percentage, some, portion, if you want, of the probability distribution, okay? So, right, so you can use for this the likelihood ratio, okay? So I talked about likelihood, I talked about squared. I defined both, so you may have seen that you can express the likelihood as minus chi squared over 2. Look at the two definitions that I gave you and see that that's true. And you can use, in general, you want to maximize the likelihood or minimize the chi-squares, the same thing, because they are related like this. So likelihood or minimum chi-square, you will have the best fit model with the best fit parameters, okay? But that's not the only thing that you want in life, to have the best fit parameters. You also want to quantify what are the confidence level regions for each parameter, and in particular when there are many parameters, okay, you want to know the probability distribution function of the parameters. So you can use for this, to calculate confidence level regions, you can use the likelihood ratio, okay? So basically what you do is the following. So you use the likelihood ratio. Okay. And what you do is to calculate the likelihood at a particular point in parameters, and you compare it to the likelihood of the best fit parameter, okay? So a model is acceptable if the likelihood ratio is above a certain threshold. So you will have chi-squared minus the minimum chi-square, which define the best fit parameter, okay? And this will be equal to minus 2 log likelihood over maximum likelihood. Maximum likelihood and minimum chi-square is the same thing, okay? So, okay, again, I'm assuming that the parameters have Gaussian distribution, which is not always the case, but we will make this assumption to continue having beautiful Gaussians and making our lives easy, okay? At least for this hour. Okay, so what's the procedure? You can, you can find the maximum likelihood. Then you go down the likelihood distribution. Imagine the likelihood is a Gaussian. You go down the likelihood distribution till you enclose a certain percentage of stuff, okay? And you can, so basically you go down the likelihood until, if you want to calculate the 1 sigma confidence level, you go down until you enclose 68.3% of the total, yeah? Until you enclose, for example, 68.3% of the total for the so-called 1 sigma, okay? Let's say you want to find the 1 sigma confidence level limit. I will take questions in 1 second. Let me write down this. So, and imagine the likelihood is Gaussian, okay? So then you want to find, so you have this beautiful likelihood here. You want to find the point A and the point B, so this is the likelihood at its maximum, okay? So you want to find where likelihood, the points A and B, where the likelihood is the same, okay? It's a symmetric function, everything is beautiful, and the integral between A and B of the likelihood of x dx, this is equal to 0.683 times, the total integral, okay, Lx dx. We call this a 1 sigma region between A and B, okay? So here you will have, I don't know if to erase this, but you may have some alpha best, this is the best fit parameter, alpha sub A, alpha sub B, okay? It's the 1 sigma region around the best fit in this case, okay? Okay, other typical values that you could take into account. Can I move on to another page? Well, in any case, this is What happens?
The variable, the integration variable, what are we integrating over?
Over a parameter. X is a parameter here. Yes, X is a parameter. So just to mention another, so you may take the 68.3%, you may take the 95.4%, you may take, the 9.7% or 8. These are the 1 sigma, 2 sigma, 3 sigma confidence level regions. These are other choices for different thresholds. So I take question. I think Lima had a question. No question. It was what do you integrate over? And there was another question. Greco. If I can go back to the previous board? Yes? Here? Go down the likelihood until you enclose 68.3% of the total. Until. Yeah, that was a very specific question. Yes, sorry, there is a question in the back.
When you write this equation, chi-square minus chi-square minimum, what do you want to do after that? You want to minimize the chi-square, this difference to achieve the best chi-square possible?
Oh, so there, to take the likelihood ratio, what I was saying is that what I have to do there is to calculate. You can use, what I was saying is that you can use the likelihood ratio to calculate different confidence level regions. Yeah? To calculate how far you are from the maximum likelihood or the minimum chi-square.
To do that, you have to have the actual maximum likelihood.
That's right.
Oh, okay.
Yeah. And we will use the likelihood ratio also to update our models in each step in a Markov chain Monte Carlo likelihood analysis. I think tomorrow we will do that. Yes? Yes. Next topic, but since it's I will talk about combining different data sets, analyzing over parameters that may come from different data sets, but I will leave that for tomorrow. So I'll take questions now. Yes, Eric.
Just a question, a little confusion. When you want to compute the confidence interval, legitimately are expected to use the posterior distribution. But here, when you use the radial likelihood, is because
No. Here I'm not using the posterior distribution, right? I'm trying. So well. Wait. So what's your question again?
it's because when you try to compute like the confidence interval for the parameters space,
Yeah.
expect to use the posterior.
Yes. That's correct. Yes. Sorry, I misunderstood the question. That's correct. Because I'm integrating over the parameters, right? So I have the posterior distribution of a particular parameter, and I want to know what's the 1 sigma or the 2 sigma or the 3 sigma enclosed interval for that parameter. So in that case, I use the posterior distribution. Didn't talk about marginalization over different parameters. So here in this model, I use parameter, okay? Talk about marginalization and combining different experiments tomorrow. Susana.
No, there is a question
From
from YouTube.
YouTube?
Yes.
Okay.
In what case is it okay to have non-Gaussian
In what case is it okay to have non-Gaussian
distributions?
distributions? For example, well, I understand that the question is, what cases can you have non-Gaussian distributions? And you may have non-Gaussian distributions, for example, in the CMB at low L, where you don't have the central limit theorem kicking in, you have a few modes. So in that case, you cannot approximate the likelihood as a Gaussian, right? The central limit theorem is not kicking in. The CL distribution is not Gaussian. So you will have the likelihood distribution given by something else. In general, when there are a lot of data sets, whatever you're studying, the central limit theorem works well. But when whatever data set you have, when you don't have a lot of data points, the central limit theorem will not be valid. So, if the distribution of the particular data points you're studying is not Gaussian, which may be very well the case, then the likelihood is not going to be Gaussian. Yeah, that's why the analysis of the CMB, for example, divides between L less than, 32 and greater than 32. They just put, okay, so for large scales, they don't make this approximation of the Gaussian. Augusto had a question, sorry, and I have been, yeah.
Yes, my question is the last right integral.
Yes?
Yes. For definition of the likelihood, like it's a probability, is 1 on that integral.
Yes, it may, yes. If it's well normalized, it should be 1. Sometimes it's not well normalized, that's why, yeah. Correct. If it's a probability, it should be 1, but it may not be well normalized. Yes, question, what's your name?
Pablo.
Pablo.
Again, why are you integrating over the likelihood and not over the posterior?
It's the posterior. L here is the posterior. Sorry about my notation. Yeah. Question, what's your name? Juan.
So if you want to compute the confidence levels of a non-Gaussian distribution,
Ah, that's a story, yes.
yeah, but the idea is like to do the same procedure. I don't know.
It will not work, right? Because if it's asymmetric, the distribution, you will not find where, this thing see, I will try to be cool and do this. This thing will not work, right? So how do you present your results when the likelihood is non-Gaussian? It depends on how your likelihood looks like. Now, for example, I will give you one example, but it's not, this is only applicable for a Gaussian where the L of A is equal to L of B, but perhaps your likelihood looks like this. So for example, I know, okay. So for example, the probability, let's take the tensor to scalar ratio, okay? Which you may have seen with Julian, or yeah. This is the probability distribution, okay? This is not Gaussian. It has a prior, a physics motivated prior at 0, okay? So you cannot give here 1 sigma confidence level limit. What you can do, and people do, is when you go, say, 95% of the 95% of the curve. Say you enclose here 68% of the curve, and here you enclose 95% of the curve. So you report these results, yeah? So it's like, the maximum, so R at the 95% confidence level region, or the R, the tensor to scalar ratio at the 68% confidence level region, yeah? But it's not an interval. It's just a value that you report. In this case, that's one example of something that happens, in the literature. I mean, it depends on the shape of your likelihood you're going to report.
Yeah, so I'm kind of confused. I don't know, if I have a PDF and integrate it until, 70% of the total
Then,
curve, area of the curve,
yeah.
do I have then the value with 68% of accuracy?
Yes?
Okay.
Yes. So by this, that all of this is 68. Okay, Lima and then Eric. No question. Okay, Eric.
When the papers, they inform like, I don't know, maybe asymmetric errors also, like
Sometimes the papers give us errors. That's another thing that could occur, right? Sometimes you have plus minus, plus some value minus some other value. That's also possible, yeah? Where you just, give the error with respect to the best fit or to the mean, okay? You go in both directions, and yes, you have different values. Other questions? Okay, what's your name? Facundo.
In the chi-square distribution, the nu is the number of degree of freedom.
That's right.
Meters of the data, or which parameter?
The number of degrees of freedom of the parameters, so the degrees of freedom of the distribution that you're considering, right? So what I said nu there was the degrees of freedom in general. I was writing a generic chi-square distribution. But then I wrote n minus m because I was saying that I was considering a certain data with n points and a parameter that has m different parameters. Yeah. Maria Pia. Yeah, they tend to be different values, not necessarily the case, right?
So in that case, you should choose how to report the.
Yes, as long as you're clear, there is no as long as you're clear in what you're reporting, all good. What is the most used? I don't know. If I tell you, I lie because there are different ways in which people report. I tend to use the mean, but just whatever. If you get a posterior that is not perfectly Gaussian, then you will also have to report. As long as you're clear in what you're reporting, that's fine, right? There is no rule that you have to, but it's, people want to summarize a curve into some numbers, so as long as you're clear into what numbers you're summarizing, that's good. You have a question. Yeah, yeah.
Since this is a theoretic operation, is something that approaches with another quantities, statistics, I was wondering if there are some common misconceptions about interpreting this latitude radio and one accurately.
Common misconceptions. Not that I can think of. Not that I can think of. I think it's very standard. What I talked about today is super standard. Yeah. Let me think about it if I can think about a misconception. But yeah, I don't think for these that are really misconceptions. It's like kind of the bread and butter of statistics these days, yeah. Yes. But I think, are there more questions? Okay. Well, then I will see you tomorrow.